Hi, everyone. This is part two about processes and threads. We start with the concept of process. Actually, this part is rather long. Therefore, I cut the discussion of the process basics into three components. The first one is about its basic concepts. The second one will talk about how to create and use processes. The last one will deal with shared memory. So you may remember how you compile a program from a terminal using command lines. A compiler compiles your .c source files to .o files. These .o files are referred to as the object files. Then a linker will be invoked by you or automatically by your command line like gcc. This linker links all the needed .o files and other library together. The result would be a binary executable. If you do not specify the name, the default one would be a.out. We have been using them for a long time. And then finally, when you execute this a.out, right after you type return, a loader in the system will be activated. This loader loads the linked binary executable into memory for execution. Now look at this diagram. Your source code is compiled by a compiler to object codes. Usually we refer to these object codes as object modules with a suffix .o. And then a linker links all of these object modules, including the modules you used from the library, and link them into a single piece. This single piece is referred to as a binary executable. But the address in this load module are not fixed yet. Here, addresses, I mean the location of the variables and the functions. It's just a piece of quite large binary executable, a binary file. When you type a.out return, the system loader will be activated. This loader load this load module into memory. Of course, this is easily said than done. Basically, the operating system activates the loader, and the loader must inform the operating system that how much memory I need. Then the operating system allocates the needed memory to this request. The loader loads the module, this loads the module into the allocated memory. And probably the loader has to fix certain addresses that are not known before loading it into memory. Once it's done, the loader simply executes a branch or a goto to the first instruction in the load module. Then the loaded program will execute. Of course, if the operating system fails to provide you all the needed memory, the loader won't be able to load this binary executable into memory and execute. So if you are used to the GCC command line, you probably will never issue the loader command because it's all the linker uh, command because it's all there in the GCC files. But even though you don't do the linker part, it's already implicit. When you type GCC, the compiler compiles your program to .o and to .o files, and the linker is activated to link all of these .o files into a binary executable. Then, after the program is loaded into memory and start execution, as we mentioned earlier, the loader simply executes a goto or a branch instruction so that the first instruction in that binary executable will be executed. Once a program starts its execution, we will refer to the execution of that program as a process. So a process is just a program in execution. However, a process is more than a program. A program is a binary executable. But a process is the execution of this binary executables, which includes so many things you probably are not aware of. For example, a process has a program counter indicating where is the next instruction to be executed. Now, keep this in mind. I never said the next statement because we're dealing with machine instructions. So a process always has a program counter pointing to the next instruction to be executed and a step. Why we need a step will be discussed fully later. A data section and a code section. These are all referred to as the runtime stuffs. Don't worry about these items because we'll discuss it very extensively. So you create a dot out, but you could run that a dot out multiple times. For an example, you could type a dot out, ampersand, a dot out, ampersand, finally a dot out again. So one of these three a dot out would be the foreground, the last one, if you don't have an ampersand after the name. So the first two a dot outs are run in the background. Therefore, a single binary executable could be used to create multiple processes because each execution of that binary executable, a dot out, would have a process corresponding to it. So before we go on, we need to explain how a program would use memories. Here I use C, the C language as an example. Other languages may be slightly different, but usually, uh, in general, the layout would be approximately the same. So here is a program. We declare h and k to be integers, x to be double. And we have a program taking two integer arguments and returning a long type. In this program, we declare three variables, two of which are integers, one of them a float. These are the statement we put into the function A. So these are the executable statements in function A. Although we write them in higher level language, it will be translated to machine instructions. And then here, we declare two more global variables, E and F, and another function, B. So I'm sure you know the concept of global variables in C. These variables are declared outside of any function. Here we have two functions, A and B. So H, K, X, E, and F are declared outside of function A and the function B. Depending on the scope rules, some function may be able to use all of these global variables, some maybe not. But anyway, as long as a variable is declared outside of a function, it is a global variable. Variables declared inside a function, for an example, A, B, and C inside a long function A. These are referred to as local variables. If you remember the concept of C carefully, you know these local variables can only be used in the function in which they are declared. For example, in here, lowercase a, b, and c, these three variables can only be used in this long function a. They cannot be used in this integer function b. Even though you declare another int a and b here, this a and this b will be different from this a and this b, because this a and this b are associated and can only be used in this long function a. And if you do have an integer a and b here, this a and this b are local variables of this integer function b. So this means local variables can only be used in the function where you make the declaration. Outside of the function, they cannot be used. Even though two functions, you declare two variables, one in each function with the same name, they are two different things. If you do not remember this, please open your C textbook and refresh your knowledge. And finally, we have these statements here and this statement here. These are code. These are codes. They are executable instructions, or eventually they will be translated to machine instructions. Now, it's very interesting to understand the following two concepts here. After compilation, say, suppose we have this file, .c, then the compiler will compile this file to a .o. After compilation, the compiler knows how many global variables are there. And from these variables, the compiler is able to determine the total size of the global variables. Suppose each integer requires 4 bytes, and each double requires 8 bytes. Compiler would treat H, K, E, and F as 4 integers, each of which has 4 bytes. So for H, K, E, and F, there are 16 bytes. And now X is a double. And suppose it uses 8 bytes. So in total, compiler immediately knows there are 24 bytes for the global variables. And the codes here, right after translation, the number of instructions and the size of instructions are known. Therefore, after compilation, the size of these codes in each function is known. Then you link all of these .o files together into a binary executable. Because those global variables, the size of those global variables are known, the linker easily can calculate what is the total size of all global variables declared in all .c files? And the linker, after linking, it knows the size of each function. And adding the size of these functions together, the total size of all functions is also known. So let's quickly refresh this. After compilation, the compiler knows the size of all global variables in that file. After linking, the linker knows all the size of instruction. Therefore, the total size of the code and the total size of global variables are known after linking. Of course, the compiler also knows how many bytes are needed for function A and how many bytes are needed for function B. But because function A is not run, the local variables in A, such as A, B, and T, will not be allocated. This will be explained later. So for this slide, always remember, after linking, the total size of global variables and the total size of the instructions are known. The sizes of these two sets of items are fixed. But in C, we have something more. I am sure in your first C programming practice, you know how to allocate extra space by the use of these two functions, malloc or malloc if you like it, or calloc or calloc. Different people may pronounce it differently. So suppose I have a function, a double function k, in which you call malloc to retrieve, to request a 2k size of extra memory. The pointer to this 2k area will be returned by malloc and saved to a pointer p. So how does this malloc memory allocation perform? Now look at the right-hand side. There is an area in memory when your process runs. It's referred to as a heap. This heap, the concept of heap here, has no relations whatsoever with the heap in heap sort. They are two different things. So when your program runs, it becomes a process. It would receive an area. We call it heap area. Every time when your program directly or indirectly calls malloc, calloc, or some other functions that requires the allocation of a piece of memory, the system will search this heap to find a usable space for that. For an example, suppose we have a heap area going from minimum address to maximum address. And in this heap area, we have some area used, either through previous calls to malloc or calloc, or some other mechanisms. Anyway, they are used. So between two used areas, there could be free areas. For an example, we have one free area of 1.5K, a free area of 3K, a free area of 1K, and a free area of 0.5K. So when we call malloc to get a 2K free area, there are various algorithms available for malloc system to use to find a usable area. Let's take a very intuitive approach. We just search all of the free areas from minimum address to maximum address. Say, first one, we see 1.5K. Is it large enough? No. Then we go for the next one. It has 3K, but we only need 2K, so this free 3K area is large enough for this 2K. What the system will do is cutting this free 3K space into two, one for this 2K, which will become used, and the remaining 1K will be free. So this is the result after cutting the original 3K free space into two, one used, and the remaining 1K free. The pointer to this used area 2K will be returned through this malloc at the save2 key. So the memory area for malloc and calloc is referred to as the heap. So we know a program has a global variable area, an area to store the machine instructions, an area for malloc and calloc and all alike to use. So we learn three. The fourth one is probably more complex. It's called the stack. Let me provide you with a intuitive explanation. You probably have learned it in C or programming language class, but anyway, let me just do it to refresh what you have learned. Suppose I have four functions here. Function A has two short variable mn. In function A, it calls B. Function B is a long function in which we have a local variable character array of 20 characters. And then B calls C. The function C returns a double. And in C, it has two, a local variable, a double W, and a long T. And finally, function D, which is an integer function. It has two local variables, U and V. Always remember, these local variables can only be used within the function in which they are declared. Outside of that function's local variable cannot be used. So we can immediately derive the following concept. When I call a function, all local variables of that function must be there for that function to use. After that function returns, do I have to keep those local variables of that function there? Definitely not, because I'm not going to use it. So the existence of local variables of a function goes as follows. When that function is called and the control enters that function, before the first statement of that function can be executed, all of this local variable must be allocated. Then the function starts its execution. Upon return, all of those local variable can be erased because I don't need to use it. So now let's say the main program calls C. Please refer to the functions here. When main program calls A, then its local variable m and n must be available. When A calls B, then B's array, B of 20 characters, must be available. When B calls C, W and T declared in C must be available. When C returns, W and T are no more needed. When B returns to A, the character array B will not be needed. when A returns, M and N are not needed. So did you find something very interesting? When we call function call main program to call A equals B equals C. And C returns first back to B, and B returns back to A, and then A returns to the main program. Therefore, this call sequence has a first in, last out order, isn't it? Now, because the allocation and the free of this local variable simply goes parallel with the function being called and function returning, therefore, the allocation order of local variables is also first in, last out. Or if you want to say it in a different way, that's last in, first out. So let's explain it with a diagram. So the main program calls A. So when A is called, its local variable must be M and N, and that has to be allocated before the statement in A can be executed. Now, what does that mean by first in, last out, or last in, first out? It is a stack, right? So let's say we have an area in the system. This area is used to store A's local variable. And because allocation free of these local variables follows a first in, last out order. So it's a stack. So I have a top here. Now, in A, it calls B. We have this. So B's local variable, the array B, must be allocated when B starts running. So from main program to A, we have A's local variable. When A calls B, we have B's local variable. So the top of this stack goes down. So in other words, you could say it this way. When B is called, the area that contains B's variable will be pushed into this stack. Then when B calls C, we push C's local variable area onto this stack, and the top pointer is here. Now we are in C. Now suppose C does not call any function, and C, after doing something, C returns. So the area originally occupied by C's local variable would not be needed. It could be simply freed. So the top pointer goes back to where B was. And then when B returns to A, the local variable area for B could be freed. And the top pointer goes back to A. So as you can see, the coming and going of these local variables of functions simply follows a stack operation. Now, what if in A, function A calls D, A equals D. A equals D is not here because I don't have space to put more statement here. So A calls D. And because D is called from within A, so A's local variable must be there because A hasn't returned. Then when D is called, D's local variable must be available. So the area that contains D's local variable is pushed onto this stack, and we move the top pointer from here down to here. Now, that's what we have learned. The call return sequence is a first in, last out order. Or if you like it, you may want to say last in, first out order. This is a stack. To allocate memory for local variables or functions, we need such a stack. The size of this stack is unknown. Why? If you have a function that may call itself in a recursive way, so its local variable will be pushed onto the stack over and over. You don't know how many recursive calls to that function will be. Therefore, the size of the stack is unknown. By the same reason, the size of heap is also unknown because you call malloc and calloc usually in an unexpected way, completely depending on your program execution logic. This is referred to as dynamic allocation. So we need a heap for dynamic allocation. We need a stack for these local variables, that is first in, last out order. So we have learned 4 important things when your program executes. Once you know this, when you type a.out and return, the loader would ask the operating system to give you a section of memory. This is referred to a process space for your program. The first part, the text or code section, contains all of the instructions in your program because the size is fixed. The size here will never change. And the data section contains all of your global variables. And the size is also fixed. Now, for those 2 unknown size, the heap and the stack, the allocation usually goes as follows. Right after data, when you want to dynamically allocate something by calling malloc calloc, the memory goes up. So you need something new, it's here. When you need something new, it's here, and so on. Now the stack pointer goes down. This is exactly what those diagrams shown on previous slides. When you call a function, the function's local variable will be pushed down. So when the top pointer of your stack and the top pointer of your heap meet with each other, it means you run out of space. You run out of space. And next time when you call a new function, it will tell you, sorry, no space or insufficient space. Or next time when you call it malloc asking for a piece of memory, and you don't have extra space to use. In should that happen, your program could be killed. So how allocating stack space is pretty easy. We just push those local variable area onto the stack. But allocating and freeing space in a heap requires some further understanding, which will not be discussed in this class. You will learn it in an operating system class. Now, this is based on one very interesting concept. That is, your program will never modify it yourself. You may want to say, how could that happen? A program could modify itself. Yes, it did happen in the good old days in programming. As we mentioned in previous lectures, in the 50s, the 60s, even the 70s, computer memory is very small. So programmers learned some bag of tricks, allowing a program to modify itself, that's generating the next version of this program and run it. So in that case, the size of your program may change dynamically. But in modern days, if your program is written in higher level language, the code section after compilation is already fixed. Now, After knowing process space, we need to learn a bit more before we could talk about fork to create child processes. At any moment, a process running in the system can be in one of the following 5 states: new, running, waiting, ready, and terminated. A process in a new state means that process is being created. Why a process being created is so important? You type a dot out, and the loader brings your program into memory, but that is just load a binary file into memory. The operating system must do a whole lot of things so that your program can run. For an example, open std_in file for you, std_out, and stderr, and probably other things. So it takes some time, even though it could be very short amount of time, your program cannot run. So that is when your process is in a new state. Once all the needed resources have been allocated, and if the CPU is free, your process is allowed to run. In other words, your process has a CPU or a CPU core and runs. That is in the running state. The waiting state means your process is waiting for some events to occur. What are these events? An example would be waiting for input-output completion. Remember, in our first lecture, we specifically mentioned that when a program is doing its input-output, the program has to be suspended. But there are a whole lot of things for a process to wait. For an example, a process wants to create a child process. Before that child process can run, do you want the creating process to wait? Or if process A needs a piece of information from process B, and if that piece of information is not yet available, you probably have to force process A to wait until that piece of information will become available, and so on. So this waiting, that's why we say waiting for some event to occur, rather than very strictly saying waiting for I/O completion. Never ever say that, because it's so restrictive and incorrect. The ready state means the process has everything but the CPU. That is, if a CPU is available, that process could run, but not necessarily it can run. Because as we mentioned, when we talk about interrupt, there is a thing called a CPU scheduler, which determines which process can run. The CPU scheduler, when it sees a CPU or CPU core is ready, it checks all the states in the ready state. All the processes in the ready state and file one to run. So essentially, a process is in the ready state. It means it is waiting to be assigned to a processor. But here, in the waiting state, it's waiting for something in addition to a CPU. Finally, the terminate state means the process has finished execution because that process may have already received some resource allocated to it when it was in the new state. So the operating system must take every piece of allocated resource back. It also takes some time. During this time, the process is said to be in the terminated states. So new, running, waiting, ready, terminate, you have to remember these 5. Now, this is referred to as a process state diagram. This is a very, very basic one. Larger system may have more states than new, ready, running, waiting, and terminated. So the new state, if a process is in the new state, that means that program is being converted to a process. And resources are being allocated. When everything is become available, so that process, what that process needs is, of course, CPU. So the system admitted that newly created process in. And because that process only needs a CPU, so initially that process is in the ready state. Then always remember, a process is in the ready state means it is waiting for the CPU. Here, process is in the ready state means they have everything but the CPU. So when a CPU or CPU core is available, the CPU scheduler simply checks all of these ready process here and find one, assign it to a CPU. So here we put scheduler dispatch. Remember, scheduler dispatch. So scheduler is the CPU scheduler. So that process is allowed to run. Now, check the previous lecture. We talked about all modern hardware has a timer. In particular, the interval timer. So after this scheduler picks a ready state for it to run, the scheduler simply set the interval timer to a short amount of time, which is referred to as a time quantum. After setting this interval timer, the scheduler simply resumes its execution. How does a schedule resume the execution of a process? Remember, we talk about a program counter. Okay, so that process will start running on a CPU. When this process is running, an interrupt could happen. An interrupt could happen. When an interrupt happens, hardware will transfer the control directly back to the operating system. One of the pieces of information the operating system or the kernel will receive is the program counter when the running process is suspended due to this interrupt. Then the operating system simply moves this running process back to ready due to this interrupt. Why the running process is moved back to ready? It's very simple to understand. If a process is running, it means that running process has everything. Now, due to an interrupt, that process is suspended. So what does that process need? Well, the CPU. Therefore, if a process has everything but the CPU, it's supposed to be moved back to the ready state. Okay, so a process may get the CPU and then run and interrupt and so on. So this is a cycle. A process may be moved a long time. Of course, it's also possible that this process runs for a while and the intervals timer goes off, that is, reaches 0. And we have a timer interrupt. And that process will be suspended and pushed back to the ready state. Or the running process wants to wait for something. For an example, this running process may want to say, I need to wait for something to happen. whether it's an input-output or something else. So in this case, it means the running process is going to wait for an event. So this process will be moved to the waiting state. Now, a process moved from the running state to the waiting state, it doesn't have the CPU, of course. In addition to the CPU, that process waits for something else, an event. So a process in the waiting state means at least two things, the CPU and that event. So when that event occurs, say the information required by the previously running process actually delivered, then this process has no event to wait. And what it misses? The CPU. Therefore, it goes back to ready. So during the life of execution of a process, from the new to ready, it simply goes through this loop or this loop and this loop and this loop so many times. How many interrupt you may have, I don't know. In a very large system, maybe thousands or millions during the execution of a longer program. Eventually, when this program terminates by calling the exit function or after executing its last statement, or this program made a mistake. So this program will be put into the terminate state. The operating system reclaims all the resource allocated to this process. After all resources are reclaimed, the operating system simply destroys this process and get the memory and so on back. After that, this process is gone from the system. So this transition diagram is so important. Remember new, the meaning of new, ready, running, waiting, and terminate. And why a process would be in ready, why a process is in running, why a process is in waiting, and how a process go from ready to running and back to ready, or to waiting and back to ready, and so on. Remember this transition diagram as much as possible and as accurate as possible, because we're going to use it over and over. This is the book cover of a very well-known book, the first edition, second edition, published in 1988. The book title is The Logic Design of Operating System. Now, look at here. The running process passes the CPU to a ready state, and this one will pass the CPU to the next one. Okay, so we have a performance manager, we have some suspended processes, and so on and so forth. And some other processes may be blocked due to whatever reason. And when you need input, you go here. When you go output, you go there, and so on. So this book cover essentially illustrate what the state diagram pretty well. Then let's go one step further. We keep saying the operating system created a process. The question is, after creating a process, that process will move among 5 states. How does the operating system know about that process, or in which state that process is in? So the operating system must do some bookkeeping. And this bookkeeping starts from a process ID. When a process is created, the operating system simply assigned a unique ID, which is an integer. We call it process ID or PID. We have seen this when we discussed the PS command. We cannot use the program name as an identification because you could run a.out multiple times. The operating system would be confused if the operating system uses a.out for identification purpose. Therefore, when you run a.out to create a process, that process receives a unique ID. When you run that same a.out the second time, you get a different ID and so on. So the operating system conceptually create a table when that process is in the new state. This table is usually referred to as the process control block, PCB. Process control block. Here I use a simple table, but in large system, we may have multiple tables organized in some data structure. So let's look at each of these items. Let's put the pointer section as the last one, because every process at any moment would be in one of these 5 states. As I mentioned, in a large complex system, there would be more than 5 states. So which state that process in would be recorded here. And the process ID assigned to that process will be stored here. The program counter, when that process is suspended due to an interrupt or due to the cause to wait for something. So the next instruction to be executed, the address of that edge will be stored here, the program counter. The program counter is not, when you go to the next instruction, it will be saved there, never. It is saved only if your program is suspended due to whatever reason. Then the hardware would know where the next instruction would be. And that where that instruction will be is an address, which is referred to as a program counter. I'm sure you have learned it elsewhere. Now, when a process executes, it requires the use of some registers. We saw that in the operating system hardware support lecture. So when a process is suspended, all the registers that process uses will be saved here. The next item is scheduling information. Why do we need it? Yes, of course. In a larger system, there could be hundreds or even thousands of processes running. Some processes are more important than the others. For an example, as a student, your process may be less important than a process created by the system administrator to handle something urgent. So this scheduling information usually means some kind of priority. When a CPU or CPU core is free, the CPU scheduler would look at this process in the ready state. And based on this scheduling information, it picks one to run. Usually, the CPU scheduler picks the one with the highest priority. And memory limits. Where I can find your code or where I can find your global variable, your stack and heap and so on and so forth. And list of open files. As you probably have learned elsewhere, there are at least 3: stdio, stdin, stdout, and stderr. There are other information. And the most important one here are process ID, process state, program counter, register, scheduling information, memory limits, and list of open files, and so on. So, because every process has a corresponding PCB, and each process may be in one of these 5 states. How does the operating system find a process? Well, simply put, all processes that are in the new state will be put together. How do we put them together? We have a pointer field. So all of those processes in the ready state would use this pointer. That is from the head of the ready state, we could trace all processes in ready state and so on and so forth. For example, if a process is waiting for the completion of I/O of certain disk, so all processes waiting for that disk to complete may be chained together through this pointer. So look at this diagram, the PCB diagram carefully. Remember this one, this one, this one, this one. All of these are important elements in future discussion of this course. Then we encounter the term process scheduling, which was used so many times. Because the number of CPUs or CPU cores is always less than the number of processes. As a result, these processes will be run in an interleaved way, so that every process will be in progress at any time. So one job for the operating system to do is to maintain the CPU utilization 100% if it is possible. This means in the server and in large mainframe computers. Because those computers are so expensive, so operating system must make sure the CPU is always busy or as much as possible in order to maximize the CPU utilization. But of course, on your personal computer, say your laptop, you are the only user. Your CPU utilization is usually rather low, probably less than 20 or even 10%. So to determine which process can do what, processes are changed into a number of scheduling queues. For an example, in addition to the ready queue, each event may have its own scheduling queue. We call it waiting queue. And even a ready queue could be split into multiple queues. So when a CPU or a CPU course becomes available, a thing called CPU scheduler inside the system would search this ready queue or ready queues to find a process and resume its execution. Let's repeat again. Hope you don't mind. How do we resume the execution of a process? Remember, in the PCB, we have a program counter. That is an address saved there when that process was suspended. That address points to the next instruction to be executed. So when this process eventually has a chance to get the CPU back and run, the operating system simply loads the address from the program counter and branch to it. And this is pretty much what the CPU scheduler will do. You will learn more about the CPU scheduling in an operating system class. If you are interested in concurrent computing, I would strongly encourage you to take that course. So how does a CPU scheduler pick process? It's always governed by a scheduling policy. Large operating system would have a very complex CPU scheduler with very complex scheduling policy. This scheduling policy is complex because it has to consider the usage of system resources and tries it's best to balance the system resource use. I won't be able to discuss it here. So this scheduling policy is unimportant to this course because the correctness of your program cannot depend on any scheduling policy. For an example, if you assume that the first suspended process would be resumed first, if you have this feeling, you are 100% wrong because that depends on the scheduling policy. We don't know the scheduling policy, so we are not able to make sure when a process would run after it is suspended. Now, the last concept here is context switch. We have mentioned the concept that a process, once get the CPU, could be suspended and taken out of CPU, and sometime later, the process may receive the CPU and resume its execution. So the concept here is about the context of a process. So what is the context of process? It's basically everything you learn in the PCB and more. For an example, in the PCB, we have a process ID, PID, process state, the value of CPU register, program counter, memory limits, scheduling policies, so on and so forth. These items constitute the execution environment. So the context of a process includes this one, process ID, process state, and register values, program counter, and so on. So if you know and remember PCB, you know what a context is. Because the context is the environment to run a process correctly. When that process is taken out of CPU, everything belongs to it will be saved to the PCB. I have a pretty good example for you. Suppose you rent an apartment this semester. So you decorate your apartment or your room by putting on some flags, some decoration, and something. And the contract will end at the end of this semester. So the landlord may want to tell you by, say, April 31st, you have to move out and pack everything up and go. So the context here is the room you have. The bed is not yours, table is not yours, but the lighting and everything may be yours, your computer, of course. So the context is your computer, your decoration, your, say, comforter and everything. So when you move out, you probably rent a U-Haul and move everything there. Next day, May 1st, the new tenant comes in. That new guy moves everything he owns into the house. That house can be considered just a CPU. So that guy puts up everything. And if you are a boy and the next tenant is a girl, definitely the decoration would be completely different. So that girl will rent that room for, say, for the summer. So she is supposed to be moved out by August 15th. After August 15th, you move back again. So on August 15th, that girl simply packs everything and put onto her car and drives away. And you, the next day, you move everything back and put it up in the original place. So this is a context switch. You simply move your context out for the next tenant to move her context in. By the time the next tenant packs up this context and moves out, you restore your context. So this is the meaning of a context switch. So after the CPU scheduler selects a process and before allocates the CPU to it, the CPU scheduler must do the following: save the context of the current running process. This running process is, of course, the outgoing one. And then put that prospect to the ready queue or waiting state, depending on the cause of this switch. Now, remember, saving the context means saving everything we list and more here. And then you pack up and moves up. The next tenant load the context back of the selected process, including the register, process state, and the PID, program counter, and everything. Now, after loading everything back, we branch to the save the program counter. Isn't it exactly the same as what we said? Use moving in and moving out as an example. But we need to do something more. Who is handle this context save and context load? Of course, the operating system, the CPU scheduler. The CPU scheduler is a system component. When it runs, it has to be in kernel mode. Remember CPU mode. Therefore, when the CPU scheduler is going to save this context, we need the mode switch to the kernel mode, so that it save the context and put the process back to ready or waiting state and load the next context. And before you actually allows the next process to run, if that process is a user process, then you have to set the mode switch back to the user mode. Otherwise, that user program will be in the kernel mode. And that user process could mess up the operating system. So remember, always remember mode switch will be needed here and here. And also figure out why. Here's a diagram showing to you a context switch. And the yellow dashed line box is the operating system. We have two processes running, 0 and 1. The blue arrow indicates running. The red arrow indicates idle, waiting for something. Initially, process 0 is running, process 1 is idle. And due to whatever reason, an interrupt or process 0 wants to wait for something, the execution of process 0 is suspended. So a context which brings back the control back to the operating system so that the CPU is in the kernel mode. So the CPU scheduler or the operating system save the context to the PCB of process 0. And then load the context from process 1's PCB. After loading it, we have a context switch back to the user mode, and then branch to the saved program counter of process 1. Then process 1 starts running. So between this point and this point, the CPU is used by the operating system. So while process 1 is running, process 0 is idle, waiting for the CPU or waiting for something else. So when process 1 is suspended due to whatever reason, a context which sends the CPU mode back to the kernel. The kernel saves the context of process 1 to PCB1 and load the context from process PCB0 for process 0. And then a context which sends the CPU mode back to the user mode, and then execute process 0 at the program counter. So this is the diagram for context switch. So here, so far we learned the process of concept of a process and the process spaces, the text section, text or code section, data section, heap, and stack, and why we need it that way. Then we explain process state and the transition diagram, followed by context switch, PCB, and so on. Please remember and go through this section as many times as possible before we move to the operations on processes next time. So let me stop here. See you next time. Goodbye.